we want to identify the independent and the dependent variable in this function right here. Now the independent variable, that's going to be the variable that appears with all the computation. And the dependent is going to be isolated over here by itself. So this value depends on what this one is. Whatever b is, we compute and generate an a. So we're going to say that the independent variable here is b, and that the dependent variable is a. Now what we're going to do in number 2 is express this equation, y equals 4 minus s, using function notation. So we can give it some name, call it f, g, h, phi, whatever you like. Let's just keep it simple. Let's call it f. And now in parentheses, we're going to put the independent variable. We're going to put s, because s is independent, y is dependent. So we're going to say this is a function of s, and it's equal to 4 minus s. Now what we're going to do here in number 3 is actually make a computation. You can see that the function depends on x, and sure enough, x is over here as our part of our computation. So what this says is that the output is equal to negative 2 times the input. Now in part A, you can see what's inside is negative 1. So we're inputting negative 1 into this function. So I think a good way to do this is just write f and then an open parentheses, and wherever we see this variable, we're going to write an open set of parentheses. So this is going to be negative 2 and then this. And now what I'm going to do is go back and fill in what I see here. I'll put a negative 1 here and a negative 1 here. So it's going to look like this. F of negative 1 equals negative 2 times negative 1. F of negative 1 equals positive 2. Let's do the same thing for f of 0. I'm going to start by writing open parentheses, negative 2. Everywhere I see an x, I'm going to write that open parentheses. And now I'm going to go back and actually put in the parentheses what I see inside this parentheses. So we're putting in a 0. So I'll put that 0 in here. Negative 2 times 0. So f of 0 equals, now negative 2 times 0 is 0. So f of 0 is 0. So when the input is 0, the output is 0. Back here, in the first part, when the input is negative 1, the output is 2. This time let's evaluate the function at 4. So I'm going to do it the same way. I'm going to write an open set of parentheses everywhere I see that x. So what I'm doing is I'm just coming back up here to the original. Everywhere I see an x, I write open parentheses. So this has already got a parentheses. Put a parentheses here. Now inside the parentheses, I'm going to put what appears inside the parentheses here, which is a 4. So let's put in a 4. Negative 2 times 4. So we're saying that f of 4 is equal to negative 8. So when the input is 4, the output is negative 8. Now here in problem number 4, we have a new function. We're calling it g, and the independent variable is y. So the inputs are going to be called y, and we can see over here what to do with it. Whatever we put in, there it is, we multiply it by 5 and subtract 3. So now let's compute g of negative 2. So I'm going to do it like I do all of these. I'm going to write the g, and wherever I see, back up in here, wherever I see the independent variable, I'm going to write an open set of parentheses. So g of something equals negative 5 times something minus 3. And now I'm going to put that something in. I know what that something is. It's negative 2. I'll put it here, and I'll put it here. So we're going to get g of negative 2 equals negative 5 times negative 2 minus 3. This is 10 minus 3. So g of negative 2 is 7. Well, we've taken it up a notch here in number 5. Here's a function. We're calling it h. The independent variable is x. So we're saying that the output depends on x. And here's what we do to get the output. We'll do this to x, square it, multiply by 2, subtract 3 times the x, and then add 4. And what we're asked to do is input negative 4/5 into here, do all this work, and see what we get out. So as usual, I'm going to write h and then open parentheses, wherever I see the variable, equals 2, open parentheses squared, minus 3, parentheses, plus 4. Now in each set of parentheses, I'm going to put that negative 4/5 and then compute. So let's put it in. We'll get h of negative 4/5 is equal to 2 times 4/5 squared minus 3 times negative 4/5. That's a negative over here, right? Negative 4/5, plus 4. Now it's a matter of computing. So let's compute the exponent first. So we'll get this is equal to 2 times, now negative 4/5 times negative 4/5 is positive 16/25. Negative times negative is positive 12/5, and then plus 4. And now in the first term, 2 times the fraction, whole number times the fraction, just multiply tops together. So we are going to get 32 over 25 plus 12 over 5 plus 4. Now we're adding 3 fractions. They all have different denominators. So the LCD here, let's get a common denominator, is 25. So I'm going to turn this denominator into a 25. There's really a 1 here. Turn it to a 25. So we are going to get 32 over 25 plus, now this is going to be 12. I want this to be a 25. So if I multiply the bottom by 5, I have to multiply the top by 5. So 12 times 5 plus, now this denominator up here is really a 1. So to get it to be a 25, I'll multiply by 25. But that means I have to multiply the top by 25. All right, now 3 fractions, same denominator, 25. Let's see what we get in the top here. 32 plus 12 times 5 is 60, plus 4 times 25 is 100. And then adding these together on the top, we will get 192 over 25. So we will conclude then that h of negative 4/5 is equal to 192 over 25. Now just more computation here in number 6. We're given that the output depends on x, and it depends this way. We're going to square x, multiply by 9, and subtract 15. Now we're asked to find the output when the input is 9. So let's do this as we typically do. Everywhere we see an x up in the original, we're going to have an open set of parentheses. So we're going to write g of, there's the x, open set, equals 9. There's an x, open set, squared minus 15. Now, let's put in the 9 here and here. So this is going to give us that g of 9 is equal to 9, and then a 9 goes in there, squared minus 15. That's equal to 9 times 81 minus 15. 9 times 81, 729 minus 15. So we're going to say that g of 9 is equal to 714. So what's happening here is that we have a relationship that does this. When the input is 9, the output is 714. You put in a 9, you get out 714. And in number 7, f of x is 3x squared minus 5x. Let's find f of 0. So as we typically do here, let's write f open parentheses equals 3 parentheses squared minus 5 parentheses. And now, in the parentheses, we will put the 0 here and the 0 there. 0 will go into each one of those parentheses. So we're going to get f of 0 is equal to 3 times 0 squared minus 5 times 0. Well, this just gives us 0. So what we're saying is that f of 0 is 0. You put 0 in, you get 0 back out. So we're going to take a look at number 8 and do just what we did in the previous problems. We have the function is equal to, the output is produced using this set of instructions. 3 divided by the input, plus 3. So let's give it a try here. So we'll write f, and there's the x, so open parentheses, equals 3 over, open parentheses, plus 3. Now in the parentheses, we are going to put the 9 here and here. I'll do it up here. So we're going to get f of 9 equals 3 plus 9 over 9 plus 3, 3 over 12, and we can reduce that. So let's say that f of 9 is 1/4. And what it means then is when the input is 9, the output, that whole collection of symbols represents the output. When the input is 9, the output is 1/4. Now we're given this equation right here. Y is equal to plus or minus the square root of x minus 8. And we want to know if this equation defines y as a function of x. So keep in mind now that what a function does, it takes one input and takes it to exactly one output. One in, one out. Now, do you see what's happening here is that if we take an input, suppose we take a number for x and put it in, we'll subtract 8, take its square root, but then what we get is we get positive that number and negative that number. Here's what I mean. Here's an example. Suppose we put in a 12, so I'm just picking 12 because it'll work nicely. What happens if x equals 12? So what we'll get is that y will equal to plus or minus the square root 12 minus 8. Y equals plus or minus square root of 4. Y would equal plus or minus 2. And what's happening here now is that one value of x, namely 12, goes to two values of y, right? You put in a 12 and you can get back a positive 2 and a negative 2. So we're going to say, no, not a function. How about fn for function? Function of x. What we want to do now is find the domain of this function. So here's the rule for converting an input to an output. So find the domain. In other words, what input values can we use to make this thing computable? So what if we put in a 0? Would that work? 0 plus 2 is 2. Square root of 2, that exists. What if we put in negative 2? Well, if we put in negative 2, we'll get negative 2 plus 2 is 0. Square root of 0 is 0. That exists. That's computable. What if we put in negative 3? If I put in negative 3, I'm going to get negative 3 plus 2 is negative 1. Square root of negative 1, not a real number. So negative 3 is not part of our collection of input values. So here's how we'll find this. Because this is a square root, we know that we're taking square roots of non-negative numbers. Non-negative meaning positive and 0. No negatives. So what we have to have here is that we have to have that x plus 2 has to be greater than or equal to 0, right? That's how you say non-negative. So we can solve this. Let's just subtract 2. So we'll get x greater than or equal to negative 2, and that's it. There's our values of x. So if we use negative 2 or anything bigger and put those values into here, this whole side is computable, and we'll get an output. Now, in problem number 11, we're looking at a voltage across a resistor, and we're told that it varies directly. Okay, now there's a model for direct variation. You've probably seen it in your textbook, but the model for direct variation goes like this. Y varies directly as x. So this number k, that's called the constant of variation, or the constant of proportionality. So that's what we have. We have this type of relationship here. Now, in our particular case, we're given that the voltage varies directly as the current. So using our particular letters, we're going to say that V is equal to K times I. Now, here's what we know. We know that we have some values for V. Now, V is equal to 60 when I equals 5. So what we'll have is 60 is equal to K times 5. See what I'm doing here? I'm putting the 60 right in here and the I right in here. 60 equals K times 5. And now let's just divide both sides by 5 and we will get K. So we're going to divide by 5. We'll get K equals 12. So we can now say, let's go back here, Here's our general variation equation, V equals Ki, and now we have a specific value for K. So now what we're going to say is this. We're going to say that V equals 12I. All right, but now we need to be careful what we have here. What we've written is that the voltage is a function of the current. V isn't given in terms of I. So our independent variable is I. The dependent variable is V, so V is given in terms of I. We have V as a function of I. But what we want is we want to express the current as a function of the voltage. We've got this just backwards. We've got the voltage as a function of the current. We want the current as a function of the voltage. Well, we can isolate I if we just divide both sides by 12. All right, so this last problem that we're going to do says that art club at a community college is selling burgers at lunchtime for a fundraiser, and they spend $12 for condiments and supplies. So that's a fixed cost. $12, that's fixed. Then the cost of the meat and the buns for each burger is 65 cents. So what's variable here is the number of burgers that they make. So what we want to do is express the total cost of the number of burgers, X. So we're going to have something like C of X. So we're going to have C depends on X, right? What this says is the total cost depends on X, the number of burgers, and this is going to be equal to, if we sold 2, it would be 2 of those 65. Now the of is a multiplication. 2 of 65, 2 times 65. If we sold 5 of those, we would have 5 of the 65s, 5 times 65. If we sell X of them, we are going to have, I'm going to write it down here, we're going to have X of those 0.65. But I'm going to write that like this, 0.65X. And I think that's it. We've got it. So the total cost is going to be $12 plus 65 cents times the number of hamburgers that we sell.